plenty of water and air, ideal conditions for rusting. But not with the metal they are looking for. Gold, one of the few metals found in its natural, shining state. Most metals are found as oxides or sulfides that are dug out of the earth as lumps of ore. Pentlandite, a nickel ore. Chromite, a chromium ore. Molybdenite, a molybdenum ore. And hematite, an iron ore. The metal is separated from the oxygen or sulfur by an ore refining process. Iron ore is refined in blast furnaces. Unfortunately, iron will try to recombine with oxygen if the conditions are right. The iron atoms join oxygen atoms in the air to form a surface film of iron oxide. This reaction occurs slowly at room temperature, but as you can see, the iron oxide film forms quickly at higher temperatures. Chromium forms a different sort of oxide, one that protects it from further oxidation. Chromium atoms at the surface ionize, and the electrons released reduce oxygen molecules in the air to oxygen ions. The oxygen and chromium ions then react to form chromium oxide. This oxide protects the surface from further oxidation by slowing down the diffusion of chromium and oxygen ions through it. If a steel contains enough chromium, its oxide film acts in a similar way. The room temperature oxidation of iron is speeded up if it is wet, because iron ions are very mobile in water. They combine with hydroxyl ions, formed by a reaction between oxygen and water, to produce hydrated iron oxide. But this does not protect the surface, and corrosion continues. When a steel contains at least 10.5% chromium, it produces a chromium-rich oxide. This not only adheres tightly to the surface, but it also has such a low diffusion coefficient that further wet corrosion is prevented. It's called the passive film. If the passive film is accidentally removed, the exposed stainless steel reacts with oxygen to form a new one. And the protection is automatically restored. Over 100 grades of stainless steel have been developed to solve the world's corrosion problems. If used correctly, stainless steel can be almost as durable as gold. But if mistakes are made, two basic types of corrosion can occur. The first is uniform corrosion, where all the stainless steel in contact with a liquid corrodes at approximately the same rate. Thousands of tests have been done to identify the right stainless steel to use with different liquids. And it's easy to avoid uniform corrosion by referring to the results of this work. The second basic type of corrosion is caused by local breakdown of the passive film. One reason for this is often the presence of chlorides or other halides in the working environment. A small pit forms where the breakdown has occurred, and corrosion continues until the steel is either perforated or the site repassivates, or the oxygen supply to the cathode region is diminished or stopped. This problem can easily be avoided by specifying a suitable higher alloy stainless steel. Passive film breakdown may also occur in a crevice. In such locations, convection cannot take place, and only mass transport by diffusion is possible. When this happens, the local environment changes. The stagnant liquid becomes more acidic, and its metal chloride concentration increases. Eventually, the passive film becomes thermodynamically unstable and is destroyed. The unprotected surface then starts to corrode. This problem can be avoided by using a stainless steel containing higher amounts of chromium and other alloy elements such as molybdenum and nitrogen. Stress corrosion is particularly dangerous because there may be no visible sign of corrosion occurring. As the name implies, this type of corrosion can occur in some stainless steels operating under a tensile stress in a bad environment, usually one containing a halide. Cracks form after an incubation period and then propagate rapidly, causing fracture to occur. Big improvements in stress corrosion resistance can be obtained by using either a ferritic, a duplex or an austenitic stainless steel with a high nickel and molybdenum content. This type of localized corrosion can occur in both an acidic and a neutral chloride medium. It used to be a problem, but it has now been eliminated by modern steelmaking techniques. As you may expect, a piece of stainless steel normally has the same chemical composition at any location. However, if it is heated to between 500 and 800 degrees Celsius, particles of chromium carbide could start to form at grain boundaries inside the steel. If this happens, the chromium content decreases at locations near the carbide particles. The total chromium content hasn't changed, but the chromium atoms are no longer evenly distributed. There is insufficient chromium at locations near the carbide to produce a passive film, and corrosion occurs along the grain boundaries. Modern steelmakers have eliminated the problem by producing stainless steels with such low carbon contents that much fewer carbon atoms are available to form the carbide. This not only reduces the number of chromium atoms required, but it also slows down carbide formation to a safe rate. An alternative way to reduce the available carbon is to add elements such as titanium and niobium. They form such stable carbides at high temperatures that little carbon is left to form chromium carbide. Galvanic corrosion takes place between two dissimilar metals, but it is not usually a problem for stainless steel. When metal atoms dissolve in water, they form positively charged metal ions, and each ion leaves one or more electrons behind. These electrons produce a negative voltage, which can be measured. This information is used to rank metals and to forecast what happens when two different ones are connected to form a galvanic cell. The metal with the higher wet corrosion voltage becomes the anode and starts to corrode. When this happens, electrons flow from it to the other metal, and this becomes the cathode where no corrosion occurs. So, because aluminium has the higher voltage, it will become the anode when connected to stainless steel. This explains why aluminium rivets must not be used on stainless steel sheets. Obviously, galvanic corrosion can be prevented by keeping the metals dry or electrically insulating them from each other. The keys to success are, first, to quantify important factors of the working environment, and then to select the most appropriate grade of stainless steel to resist general corrosion. The second step involves using a combination of design skills and knowledge of stainless steel to avoid introducing localized corrosion problems. For example, this problem could have been avoided if the designer had eliminated the crevice by specifying stud welded bolts. Another solution could have been to use welds instead of bolts. For many architectural applications, a suitable mastic is often used to eliminate the crevice in mechanically fastened joints. Similarly, a sealing weld run may be used to eliminate the crevice in this type of welded joint. The local environment can also become more aggressive if sludge buildup occurs. So, good designers always eliminate sludge traps and ensure free-flowing drainage. There are many examples throughout the world where designers have combined their design skills with a sound understanding of stainless steel to produce highly successful designs. Selecting the right grade of stainless steel combined with good design is the way to ensure long, trouble-free service and advantageous life cycle costs.